number 7 for me. I, again, appreciate being able to come back and do this. We're talking today about horizontal and vertical continuous casting of copper alloys. And this, as most of the CABSO webinars, comes before a tour, an upcoming tour of Concast Industries in Ohio. In any event, let's move forward and see what we can talk about here. I've shown this slide before. Some of you may have seen it, but I just wanted to contrast the present processing of metals and materials to ancient processing of metals when we knew very little. Of course, none of us were there then, but you can see the safety equipment and the type of metal handling equipment in this illustration, which is a copy of a drawing from a wall or an etching somewhere in Egypt or the Middle East. Gives you pause. Obviously, they were melting the ore or metal over the fire. They were handling it in a crucible, which is shown in the middle illustration. And then they take that crucible out by handling it with sticks. And those bendable sticks are called withies. Very unusual but true. And they pour it into various molds. So this is casting in its basics. We do it a little differently now. And I'm going to start a little bit at the beginning. What happens in the mill or plant when we start doing things? Well, we transform various materials, scrap, pure metals, and additives, alloying additions. We've transformed those into semi-finished products for industrial use. Several steps are required for this process. And the final product usually is an alloy in a size and shape that is dictated by the customer. And that's on their order form. Well, processing in various mills can be in different forms. Many final products can be made. You can make flat products, and we've talked about those in a previous webinar, sheet strip, plate, and foil, which I didn't note. Round products, rod, wire, tube, wire being the most made product in the copper industry. Shapes, rod again, but can be all kinds of different shapes of rod. Tube with special shapes on the outside or inside, hexagons, other shapes as per requirements from the orderer. Cast shapes, cast a shape or a preparation of a cast ingot or a shape for forgings. I'd like to, as I have in many cases in these webinars, go into a discussion of copper alloys just as a background. Copper alloy designations or numbers are governed by the Unified Numbering System, UNS. UNS numbers and their system began in 1974 by under the auspices of the American National Standards Institute. The UNS system encompasses not only copper, but all metals in the United States, produced and or used in the United States. Originally, the number was only 3 digits for an alloy. For example, 260 brass was just 260. Now the number is preceded by a C for copper alloy and 5 numbers. So it would be C26000. We needed the extra digits because we ran out of numerical space in numbering alloys some time ago, and we can use those extra digits. Copper system isn't as overburdened as some other systems numbering, but it's helpful. The numbering of alloys predates 1974 when everybody was trying to coordinate and understand and categorize alloys, and they started that during and after World War II up until UNS system was developed. There are wrought and cast alloys in this system, and CDA administers the UNS copper alloy system in the United States. The UNS system is referenced all across and around the world as a basis. In fact, it's one of the few robust numbering systems there is in the world. Well, when you look at copper alloys, there's different elements that can be added to make an alloy to pure copper for different reasons. If you want to strengthen a material, you have a whole series of alloy elements that are shown at the top of this diagram: aluminum, titanium, zinc, beryllium, tin, iron, nickel, etc. Corrosion resistance. Some of those same elements are added for corrosion resistance, but silicon, tin, nickel, aluminum, manganese, iron are used. For wear resistance, you want a harder material, maybe has different characteristics. Again, you put in tin, aluminum, silicon, but there's cadmium, silver, and lead for wear resistance. Very unusual, but true. Machinability, you add zinc, lead, tellurium, selenium, sulfur, bismuth. Color. Copper is one of the only elements that has an indigenous color, metallic color other than silver gray. To change the color, you add certain elements: zinc, aluminum, tin, nickel. I would add one more, but this diagram doesn't show it: manganese. They would all tend to change the color from a reddish. Zinc tends to change it to a golden color. Tin does the same thing. Aluminum tends to turn it more white or silver. Nickel does the same thing, and manganese as well. There are white alloys in the copper family. The wrought copper alloy families are listed here as far as numerical space they inhabit. The 100 to 150 series are commercially pure coppers with very little additive materials or elements. 151 to 199, etc., are age-hardenable coppers. Again, not a whole lot of additional alloying element or elements, but a higher strength. The 200 series, copper zinc alloys, brasses. The 300 series, copper zinc lead alloys, leaded brasses. 400 series are the tin bronzes. 500 series are phosphor bronze or tin bronzes of historical significance. You can find tin bronzes, and that's the genesis of the Bronze Age in antiquity. The copper tin lead alloys are listed in there too. The 600 series, copper aluminum and copper silicon bronzes. 700 series, copper nickels and copper nickel zinc alloys, nickel silvers. Nickel silvers are called that because you add nickel and you get silver color, not because there's any silver in them. In the cast copper alloy families, commercially pure coppers inhabit a very small range up to 811. 813 to 828 are high coppers, and then 833 to 899 are essentially brasses or of various types. Some of them are trade name bronzes, but with other elements added. The 900 series are other alloys in tin bronzes, aluminum bronzes, copper nickels, etc. We have their alloy issues that have come up every now and then. Standard alloys, brasses, bronzes, specialty bronzes, copper nickels, etc. There are new alloys in the mix. Low lead alloys, silicon containing non-leaded alloys, bismuth containing non-leaded alloys. All these have been dictated and developed and put into use primarily because of the no lead rules for water handling and other activities. There are scrap issues with these no lead alloys and mixing with leaded alloys. There's also problems with alloy compositions that once you start using some of these, in other words, you need to practice with these to make them properly. That's what the information has come back to us saying. Well, let's talk now about casting, because that's what we're supposed to be talking about today. But I'm going to start with batch casting versus continuous casting. Just for definition purposes. Batch casting is where you take the metal, molten, and you pour it in a mold. The mold is cooled. The mold may be moving, but it's still just a mold sitting there. A lot of times, batch casting is done in what is called a foundry, where there are multiple molds moving around on conveyor belts, and you have the furnace with molten metal in it, pouring the metal into each mold as they come by, and then that mold continues around the conveyor belt system and is cooled, and then the casting is ejected, and the process continues. The metal structure in these types of castings consists of many large grains, not always the same size, but many large grains, crystals. The metal alloy properties vary across the cross-section of the material because of these various grain sizes of the material. These castings as a batch cast or a static cast tend to be a little more brittle, not have as much ductility and forgiveness in the material. Continuous casting, on the other hand, is a metal is poured into a mold in a continuous fashion. The cooling is provided to the mold, but the metal is moving in the mold and through the mold in a continuous manner. We'll look at that in a little bit. The product size and cross-section is dictated or is such that the metal solidifies quickly or relatively quickly. Grain structure is a little more even, although on some of these, if the product is large enough, the grains can be large. You have multiple smaller grains provided providing a more even and consistent property structure. So a great deal depends on the cross-sectional area of the product you're making and the amount of metal being poured in the die. Let's look at continuous casting grain structure, and I had trouble finding a suitable picture in a book. Here's one off of a plaque we have in our offices here at CDA. This is a billet. It's a static cast billet. A billet is a round, and they used to be produced all the time. They would be made for rod extrusions, tube, forgings, pipe, and if they were subsequently processed and made into a hollow shape, they would be pierced. But you can see all of the individual grains, and they're very distinct here, this having been cross-sectioned, polished and etched to show the grain structure. The grains start growing on the outer surface where the cooling happens and grow all the way into the center where they stop, because that's where the final solidification takes place. On another size shape, and again this is the same mounted plaque, very heavy plaque by the way. This is what's called a cake, copper refinery shapes. A cake, or the word cake, is specific to the copper industry. In the steel industry, aluminum industry, and other industries, this would be called a slab. And in fact, in many copper plants, it is called a slab. Cake is a very old terminology in the copper industry. In any event, this is a rectangular cross-sectional shape between 5 and 7 inches thick, between 25 and 36 inches long usually, and cast in one heat, one drop. I'll show you some of these in a little bit. And again, the outside is the cooling zone, and the grain structure grows, or the grains grow from the outer surface in till the parting line in the center where they all meet, and that's the final area of solidification. To make a good product, these grains or crystals need to be broken down into a finer grain structure to make the product more pliable, malleable, ductile, and many times stronger. This is actually a relatively weak structure. Here's another microstructure. I believe this is at 100x. The grains here have been processed or worked to a degree. This is gilding metal 210, 5% zinc. The grains are varying in size. This has not been worked as much as some of the other materials, and I'll show you another one here. This would be a much better structure for properties. And here's a 230 brass, red brass, 15% zinc. The structure is more even. It's been worked more from the time it was cast. Or it was cast and cooled very quickly so that the structure was more even. The horizontal and vertical casting of copper alloys and subsequent processing, I won't go into much subsequent processing, but let's talk to begin with what you start with. You start with a furnace charge, or raw material going into a furnace. And raw material in these cases are virgin metals and scrap. Virgin metals are substantially pure metals from refineries. Electrolytic copper cathode from Freeport-McMoRan copper and gold. Ingot or bars of that. You can get slab zinc from a zinc refinery. Tin in various forms, balls or sticks or slabs. Nickel in usually balls or shot. Other pure metal additions, depending upon what you're making. Or master alloys. Say you're making a copper alloy that has sulfur in it. You don't just take out a bag of sulfur material and throw it on in the melt. Most of that would go off in your hood over the melt furnace and be lost. You buy a master alloy that already has sulfur in it, copper sulfur or copper something sulfur, or maybe it's another element that you want that like aluminum. Aluminum can be very difficult to get in to a melt without it oxidizing. You might want to buy a master alloy. Makes it easier. Scrap comes in many forms. Runaround scrap. This is scrap from your own production facility. Cuttings, ends and side cuts, trimmings from slitting operations. In a regular strip sheet and plate plant, you have all kinds of heads and tails and pieces that are cut or trimmed before product is rolled down finally, or even in a wire mill. You have trimmings and cuttings and edges. All that can be taken back around. Customer scrap. If you sell a product to a customer and they stamp it, make it into something, but leave or cut parts of it away, or machine parts of it away, or take parts of it away for some reason and put it in a barrel, you can bring that back. You know the composition, you can put that back in the furnace. Saves time, saves energy, saves remelt, or a tremendous amount of remelt. You don't have to buy as much pure material. And then you get scrap from scrap merchants. This has to be vetted and carefully taken into account who you're buying it from and what you're buying, and that you don't get something you don't want in there. The use of scrap lessens the use of virgin materials, but does not decrease the need for you to, once the alloy is melted down, to check it out and make sure that you have the correct compositional parameters in place before you start pouring metal. Most materials, most metal handling facilities or metal producing facilities use electric arc furnaces these days. Here's a cross-section of a typical, but not only, type of electric arc furnace. This is a channel furnace. There are others. And in some cases, multiple electric arc furnaces are used. You're pouring from one to fill up a tundish or a holding furnace, and you're melting in others to make sure you have product continuously if you're doing continuous casting. And so we're talking about continuous casting. So this is basically a pot, a melting pot. Very large melting pot, but still a pot of molten metal. The pot is Um, you can take it down to so far, and then you have to have more. If you don't have more already available in another furnace, you could be in trouble. So many times facilities have multiple melting facilities feeding or delivering metal to one casting facility. So here's different casting techniques. I already talked about batch, which is static, vertical casting, semi-continuous and continuous. There's two types. Horizontal casting. There's really a couple types of those depending upon product type. We'll talk about that a little bit. Here's a vertical caster. This can be a vertical caster for a variety of things. Obviously, the holding furnace up above is being fed by a electric arc furnace or a metal melting furnace. The vertical caster is a high throughput, high production type facility. This illustrates that you take the metal in the holding furnace and pour it into a tundish or a very small reservoir which feeds the mold. The mold has just below it a whole series of cooling jets and water jackets, as going all the way down this string. You see there are cooling jackets and rollers that allow the product to move easily in a channel or a proper movement. Now, you can cut it off at any place. You can run this straight vertical. You can turn it like this. So there's various ways of handling this. Here's a vertical bar casting schematic. Again, the melting unit is at the side, pouring into the holding unit, which in this case feeds directly into the graphite molding die. Okay. By using multiple metal handling units, the melting unit, the holding furnace, and maybe a tundish, you have a better chance of not taking slag and other materials that may have appeared when you melted the material in the melting furnace, the electric arc furnace, into the metal itself. And that's why you pour or you cast out of the bottom. You're casting good metal out of the bottom. Any bad stuff is floating to the top and can be taken off. Okay, again, you have a water cooling jacket. In this case, the bar is coming out the bottom. You can see that this has automatic saws. Cut off. After it reaches a certain length, it'll be cut to length and then taken away to a packing facility or a subsequent processing area. And the die dictates the shape of the bar, whether it's or the shape of the product. It could be a solid bar, could be a fluted bar, could be a square bar, could be a hexagonal bar, could be a hexagonal tube, etc. The die dictates all that. Here's another way, and this is slabs or cake in the copper industry. You have charging buckets, multiple melting furnaces, with all feeding a big holding furnace, which then feeds a series of metal handling trough, or launder as it's called in the industry, which goes into a series of molds. The molds are rectangular in cross-section and fairly thick. The slabs come out into a pit, which is water-filled and has an elevator in it, which goes downward as you cast. The furnaces that usually feed this type of operation are very, very large. They're not necessarily electric arc furnaces. They can be. Many of them are reverberatory furnaces of 100,000 pounds or more if you're feeding this type of material. Anyway, this is semi-continuous casting because you have to stop at some point. The platform at the bottom of the pit ends up reaching its full travel. You have to take the slabs out, remove them, but in the process of doing this, you have a liquid metal, solid metal front. And in close-up, this is what it looks like. The gray or dotted gray area is semi-solid metal. What it says as solidus is when it fully solidifies. The word liquidus is at the liquid to solid interface. So you have a cooling zone, a zone of partial freezing. This is an illustration, and this happens in all the casting techniques. You're developing by cooling the product, the material down to a solid. You're causing the grains to grow from the outside surface into the center of the product. Depends how you cool it, how fast you cool it, how thick the product is, what the alloy is, etc. This gives you an idea that there is a zone of cooling. It is not instantaneous. On a pure copper, it might be considered to be instantaneous because that's at virtually a single point. But in an alloy situation, you always have this zone of semi-solid metal partial freezing. Very important. In horizontal casting, here's an illustration of a bar being cast in a horizontal fashion. You again have a melting unit feeding this. The molten metal is fed into a holding unit or holding furnace. The molten metal level has to be kept at a certain point or head to be able to feed the bar continuously. And this is not dissimilar from the vertical casting. You need to keep the holding furnace full to a certain point. Otherwise, it won't feed properly. You may get problems. Molten metal handling here is extremely important and critical in the integrity. I was looking for the right word, integrity of the cast or final product. Integrity is what you're looking for in the product. Solid, complete filling of the cavity, the die. You don't want any voids, any problems. You want good mixing. You do not want any areas that are unmixed if you're having an alloy like aluminum bronze. You want to make sure that the material is homogeneous, all the same. You want to bring it out slowly. And that brings up a point. The vertical casting technique is generally used for a much faster production schedule or can be used to produce material faster. Solidification and so forth can be handled faster. It also produces or is used for different alloys. Let's go back for this illustration. This particular illustration shows that there's a zone of partial freezing. And each alloy has a different zone of partial freezing. Some of them take longer to freeze or have a larger zone of partial freezing. Therefore, certain alloys cannot or have trouble being cast in a vertical fashion. Horizontal casting is much more beneficial for casting those alloys. They have to be stay in the die for a longer period of time to allow the cast structure to develop and solidify before it can be pulled out. So these alloys have to be worked on more carefully and cast more carefully. The technique, horizontal continuous casting, is not all that old, but it has been used successfully for a couple decades now, maybe 3, and it is very successful. And it's highly usable, not only in shapes, rod type formats, but in strip and slab. Here you have an illustration of horizontal casting. Again, you have a melting furnace, a holding furnace. This is highly simplified drawing. And you have a cast strip or a relatively thin material. By using horizontal casting, in many cases, the thinness or thickness can be minimized on a material, say on a strip here, so subsequent processing can be cut down if you're casting and rolling. This has been used successfully in a number of facilities and was the first usage for it, this type of casting. But also, like I said, it's used on, horizontal casting is used on alloys that need a longer time for freezing or solidification. Very important. Last thing I want to point out in casting and molten metal handling, and everybody that deals with molten metal operations knows this, garbage in is garbage out. It sounds like computer speak, and it is to a degree, but if you do not watch the type of materials that go into your casting, you don't watch the composition and monitor it carefully, you don't watch the solidification techniques and the extraction of your material, you don't watch the molds and various other things, you could end up with unusable material on the output end. And then what do you do with it? Well, you have to cut it up and throw it back in to a melt furnace, and you've wasted all that time and energy. So it's very important to start with good material, to be very, watch everything carefully. Quality control is paramount to making good material. Making good material at the end. You have to start with good stuff to begin with. Okay. Well, we've cast material, we've processed material, not all the way, but casting in many cases is the final thing. I mean, if you're doing batch casting, that's the final thing, other than maybe cleaning up the casting and machining maybe a couple pieces that fit into something else. Subsequent processing of, say, and since this particular webinar comes before a CABSA tour of Concast, Concast primarily makes rods and shapes and tubes in a variety of alloys, some with subsequent processing and others that are made in the cast form as final shape and product. Subsequent processing can vary. As pointed out in some of the illustrations we just went through, there are cutoff saws or cutoff equipment that is used in many instances to take the cast material and trim it, cut it, and then once you cut it, you put it in a bundle, or you stack it, or you bring it together and then bundle it as the customer requests. But many times there is subsequent testing, ultrasonic testing, quality control testing of various types. You may do, and usually there is. At the beginning, you have a composition test in the ladle and or in the furnace before you pour, maybe both. You want to make sure you're pouring the right alloy. You're not pouring a little bit off composition. That can change properties tremendously and be basis for rejection. So that's very important. But because in a lot of highly alloyed materials, you want to make sure you ended up with the right alloy. So a lot of plants will take a cutting or a sample and do subsequent testing to make sure they got the right alloy. It's just checks and balances. But to check a cast material, a lot of times, and even in wire and so forth, you check with ultrasonic or other non-destructive testing techniques to make sure you have the right material, the right properties, the right consistency of the material. If in subsequent processing, in many cases for rod and or shapes, is either straightening, you want the product straight before it's shipped, or you can draw it down into a thinner, smaller product, and that will change the metallurgical characteristics of the product after you draw it down or do that processing. Well, all these different techniques of treating the metal, you end up with a variety of shapes, a variety of sizes, a variety of things, and obviously a variety of alloys. Well, here you're talking about bars, rods, and most of these you're looking at are rounds, squares, X shapes. But if you'll note, and let me see if I can, there's the pointer, you get some unusual shapes here that can be made depending upon the die that you put into the casting equipment. Okay, these are all solid. These are all solid. These are bundled for shipment. They've been cut off, or in some cases the rods are smaller. They've been drawn down into a smaller size and then bundled. But you have a variety of shapes here, hexes and so forth, all in a rack or series of racks ready to be, these are in storage or prior to shipping. They may be further packaged for protection from the elements and for quality before they're shipped. These are brass, the others were mixed alloy. Here's some other shapes. At Concast you'll see many of these. These are tubes of various sizes, various shapes. On the right you see a bunch of them, or a group of them bundled together, same size, same alloy. And you'll note on, especially on the illustration photo at the right, there's little bands on these. These are movements of the product out of the die. This alloy needed a certain period of time to solidify, and it looks like 1 inch or 2 inches of advance each time. And there's dwell time in that die to allow it to solidify properly. You can read that on the side of the material. Well, what do you use these things for? You get all these different shapes, sizes, configurations, and you can look, here's some more unusual shapes in this particular area. You have tubes, but they have unusual pieces on the side or cast structure. You have channels and different sections. Well, you can take a fluted tube and that can be a gear, or you can take a solid that's fluted, drill a hole, and you have a gear. Machining. Here's another one. This one, if you can, is a gear, but it's made from a solid rod. So machining is important. Here's another gear. Here are some ferrules and various other machine parts that can be made from these things. These are high alloy, sometimes brass, sometimes various bronzes, sometimes exotic alloys. You look at a knurled nut here, but not just any one. This is an unusual one. Here's some unusual ones as well. These are all purpose-driven parts, different alloys. Here's some silver-colored alloys. Those are copper nickels, nickel silvers, or other special alloys that are white in color but copper alloy. All kinds of different things can be made. And here's some other pieces, parts that are made. This is directly from the Concast site. You have a U-channel here. You have others that are made. Here you have teeth on the inside of a hollow tube casting. Very unusual, very different. Here's a tube but with 2 legs or support sides. Very unusual casting, but that's all dictated and developed in the mold and the casting at the casting site. Okay, so I've come to the end of me talking. Well, I guess I'm going to talk some more if there are questions. And so I put up this slide if there are any questions. Otherwise, I do appreciate being able to give this discussion.
Thanks, Jim. Once again, if you have questions, please submit them using the tab on your webinar toolbar.
And let me just point out that in the past, there have been questions that have not come in immediately, like right now. You or someone else at your company may develop or think of a question subsequently, and that will lead into, well, maybe we should get a hold of CABSA and they can get a hold of Jim and he can answer the question. Well, absolutely. So that can be done as well. So if you haven't thought of something or something is in your mind but you can't put it in words right now, please submit that. Anyway.
Jim, it looks like we do have a question. All right. Do you have a rule of thumb for head pressure with horizontal casting, specifically from the center line of the casting to the metal height above?
Well, that's an awfully good question, and there is a very important, but it has to do with, and it's hydraulic pressure basically. It's head above, as the questioner is pointing out, center line or even top line of the mold in the horizontal casting unit. So the liquid metal at this point is considered a hydraulic fluid to a great degree, not just a metal that is going to end up as a solidified material. So you do have to have a certain head pressure, and it's incumbent upon the metal producing, metal handling facility, the people in the line producing this, to keep the metal at a certain height, or you're going to end up with not enough metal in the mold, not enough metal pushing the mold or the metal into the mold. Some of it is dictated by the size of the holding furnace, the feeding metal chamber that feeds the mold. The larger that is, the more the pressure will be maintained for the longer period of time. If you have a very small holding furnace or holding chamber, you're going to have to pour metal in there more continuously and be very careful about it. So the size of the holding furnace, holding chamber for the metal, is very important to be sized correctly. It has to be determined and very carefully before the equipment, or as the equipment is being ordered and developed to do this casting, that you have the right size holding furnace. Now that said, I'm using a lot of weasel words and saying I don't have a specific pressure or a distance, because it depends upon what pieces of equipment you're using. So I can't give you a number, but I know that you have to keep it up to a certain point, or you're not going to be able to fill that die and extract the metal and make good metal out of that holding furnace and through that die.
Thanks, Jim. We have another question. What causes porosity?
Well, there's several different ways to develop porosity. Porosity can be considered a gas. So again, you have to pour the metal in such a way, you have to make sure the melt is degassed, it doesn't have any entrained gas in it. Again, we go back to the size of the holding furnace, the size of the melting furnace, and how you pour the metal from one to the other will dictate whether you have entrained bubbles, gas. This is real bugaboo, not necessarily in continuous casting. Because you have that head, you have a space in the holding furnace where bubbles can float up, if you will. But you have to be very careful in the metal handling characteristics and pouring. That said, there are some elements and some materials that tend to end up with porosity. Porosity are voids, pure and simple, or a gas pocket inside the metal, entrained gas. This is more common in a static cast or batch cast product than it is in a continuous cast product. The technique for continuous casting has been developed and perfected over the years to prevent or eliminate as much of the entrained gas or subsequent porosity as possible. But that said, there are some elements that are in metals that may be entrained in metals that can develop porosity or can develop or end in the development of porosity. You also can have entrained other things, which like oxides and so forth, not necessarily porosity, but they will leave voids or bad spaces or inclusion spaces in the metal. In a wrought product or a subsequently worked product, sometimes some of the porosity, if it's very minor, can be subsequently worked out of the product or eliminated. However, in a cast product, as we're talking about here, that may or not have subsequent processing, you have to be very careful to how you pour, how you process, how you the head pressure and so forth, and the venting to make sure you don't have entrained gas. That's technique as well. Anyway.
All right, we are at the top of the hour. I do see the rest of the questions. We will go ahead and address those and send those out in the follow-up. If you think of any more questions, please email me and I will pass them on to Jen. You can contact me at, my name is Courtney Carr, CKARR at copper-brass.org. Once again, that's CKARR at copper-brass.org. Thank you again to Jen and to ABC Metals who sponsored this presentation, and to all of you for joining us. Please visit www.copper-brass.org for upcoming events and webinars. Until next time, thank you and goodbye.